So it's Friday, it's the end of a long week. We only have 60 minutes. So just to be clear on what the objective is for this session, I am not going to teach you how to do any of these things, machine learning, deep learning, NLP, etc. The idea is really just to clarify concepts, and I'm sure all of you already know quite a lot of those concepts, but there might still be things that have remained fuzzy, and different people stand at different places as to what they have learned. Since the explosion of all of this machine learning interest that has happened with the OpenAI ChatGPT, people are becoming increasingly more aware and educated about these concepts. So maybe none of it will be new, but my objective here is really to clarify those concepts so that you leave this session being clear as to what these terms mean, the very high level big picture of how things do work. And because these are things that are becoming absolutely critical in all fields of research, it is actually fairly likely that you should learn some aspects of these things for your own research. And so I will point you to some resources, mention some frameworks, places where you can actually get started and learning things. So for those who attended the sessions yesterday afternoon on R and Python, it's not dissimilar in that it's a hands-off little lecture where you can just watch and have some very easygoing, very high-level thing to really show you the big picture, and then afterwards you can go learn tools. So it's a very relaxed session. So since I said that the whole idea is to clarify concepts, well, let's start with some big definitions so that we know where we stand. So AI is nothing new, and it even predates computer, really. The idea is any human-made system, so you can even find some of those concepts in antiquity, that aims at mimicking animal intelligence. So it is an extremely huge field of study. Nowadays, when we say AI, we think of actually deep learning, things like ChatGPT. But this is only a tiny area of an incredibly large field of study. So AI is incredibly broad. And within AI, there are many things. One thing is machine learning. So that's a subfield of AI. And this is really computer-based. But again, it is not about neural networks and deep learning necessarily. It's about any computer program whose performance, so whose, for instance, predictive power or ability to give some right output, ability to classify, ability to do anything that we want it to do, improves with experience. Experience often being data. And so this includes deep learning, so the kind of things that we think about automatically nowadays when we think about AI or machine learning, but it also includes very traditional statistical inference. And so many of you have actually done a lot of machine learning in your schooling, except you weren't calling it like that at all. You were calling it with things a lot less exciting and a lot more drab. But even when you draw some regression, even when you use a very basic linear model through some data, the data is a form of experience, and you have a computer program, which is just your very simple little linear model or regression that learns from those points, learns from that experience, and you can then use that to predict where new points would fall. Like given some X values, what is the likely value of Y based on that knowledge? So very simple stats are a form of machine learning. Now, deep learning is a subfield of machine learning, and that's what is more novel. That's not the classic machine learning, and that's what uses neural networks. So neural networks are a form of algorithm, so a form of program that very loosely mimics the idea of how the brain works. And I'll show some schemes of what that look like. But the idea is to not use statistics to infer Y's from X values, but to use a form of automatic learning by an algorithm. And this sounds kind of magical, so I will show you how that actually works, and that it's actually a very simple thing, just extremely powerful. And now, what about NLP? So natural language processing is a subfield of AI that encompasses both machine learning and deep learning. So it's artificial intelligence, but that uses human language as data, because AI can be used with images and sound and just anything you want, but NLP focuses particularly on natural languages, meaning human languages as opposed to computer languages. And it can use very classic machine learning methods, such as statistical inference, which is why NLP is nothing new. But nowadays, since neural networks have become incredibly popular and powerful, it uses deep learning instead of statistics. So now, why have those neural networks become so popular in recent times? So it's because of their they're really astonishing power in doing things that we were unable to do with computers before. Because if we think of traditional programming, the way we write programs, say a Python code, a Python script, that's a form of program. We give instructions to the computer through some syntax, and we say, okay, you take some data, some input, and you're going to do this and this and this and that. So it's a set of very clear instructions that the machine can do. And machines are incredibly powerful to do that. Like, think even like a very simple calculator. It's a very, very basic machine, but it can do calculations that are incredibly difficult for the human brain. However, that power has a weakness, which is that there are tasks that just cannot be transformed into a set of instructions. If you think of a program as a set of recipe, a task such as identify a tree in a picture cannot be easily broken down into easy steps, because that picture can be a cartoon, it can be a drawing, it can be a painting, it can be a photographic image, it can be black and white, it can be blurry, it can be stylized in all sorts of ways. The tree can be of any species, any size. It can be some kind of artsy tree thing that as human we identify instantly as a tree, but that really has that high level concept of a tree, but doesn't at all look like what you see when you look through your window, if you're lucky enough to have trees on the other side of your window. So that set of tasks that cannot be easily broken down into a set of instructions, those are things that computers were not able to do. And deep learning, neural networks allow to do that by being fed a ton of pictures of all kinds, including those stylized schemes and artsy things and realistic things containing trees, and a bunch of data not containing trees, and then some labels, tree or not tree, and you feed it to some algorithm. So of course you have to build some algorithm to start with, but that algorithm knows nothing about tree. It's just some program, and I'll show what it looks like in a sec. And then you pass a ton of that data, and something happens that allows the program to be able to identify images with a tree and images without a tree without being instructed to do so. So how does that work? It's not a new concept. It started in the late 40s, but it's a concept that became briefly popular in the late 40s and early 50s as a concept, really, but didn't go very far because at the time we didn't have computing power. But now the reason there is this explosion of this resurgence of this concept, and it is actually now giving some really great results, is because we have suddenly a lot more computing power. Why? Well, because all electronics have become better, CPUs have become better, but mostly GPUs, so CPUs are processing units inside your computer that do some sophisticated calculations. And that's it's kind of like the brain of your computer, if you want. And there can be one or several of those. GPUs, that stands for graphical processing unit, that's a different type of chip that has been used for quite a long time for graphics rendering. So that's what renders the image on your screen. But some time ago, people realized that the processing of graphical images, which involves very simple calculations, very simple tasks, things much more simple than what CPU do, can be done in a GPU very efficiently, because GPUs can run a ton of those simple calculations in parallel. The strength of a GPU is that it cannot do fancy stuff, but it can do very many at the same time. Those GPUs that were initially designed to render images on a screen can actually be used to do those little calculations that are involved in those neural networks. And so GPUs started to be used as what is called GPUs, or general purpose GPUs. So GPUs used to run calculations for some program, not just to render some graphical data. And so the surge of these GPUs in this novel usage has allowed to actually revive this idea and get it somewhere. So how does it all work? There are various types of learning, and each type functions differently, but we will go at length about supervised learning, which is the main one, and I think the best one to explain the concept. So supervised learning is when you have some pairs of input and output. So for instance, images with tree with the label tree, and images without tree with the label no tree. So you have the input is the image, the output is the label, and that label data, so someone has to manually label the data. Some humans have to look at the pictures and say, okay, tree or no tree. So there is some work into creating that data, because when we say machine learning uses a lot of data, what we mean is labeled data often. So data that has non-output. And the goal is to find that relationship. So it's the same thing as regression, classification, the kind of stuff you can also do with stats. Another form is unsupervised learning. And that's something that you might have used in your start courses as well. It's a bunch of data that doesn't have label. So it's data much easier to get. It's much cheaper because you don't have to have a human label it. And you pass it through an algorithm and you try to find some pattern inside the data. So for instance, when you do market segmentation or PCA analysis or network analysis or clustering, that's what you're doing here. You're passing a bunch of data without labels. So it's not like there's no right or wrong answer in that case. And the algorithm trying to find some structure in the data. And then another form of machine learning is reinforcement learning, which is what is used in games. For instance, you have some point that has to go through a labyrinth, and it is given absolutely zero instruction on how to solve the problem. But so it moves totally at random at first, but it gets rewarded by positive points when it makes a good move and negative points when it makes a bad moves. And so the algorithm that learn how to play chess and Go and all sorts of solve all sorts of things in this way, that's reinforcement learning. They are not given instructions on how to do these things. They're just being awarded bonuses when they do the right thing and penalties when they do the wrong things. And over so many times that they can come up with novel strategies that humans hadn't thought of. So the first machines that were learning to play chess, for instance, they were given the set of instructions on how pieces move, on how to on the rules and all that. Nowadays, those systems are not given any rules. They don't even know what the goal is. They just try things at random. And through this reinforcement learning or of penalty and reward, they can come up with astonishing things. But how does it all work? Because the way I've been talking about it for the past 15 minutes, it sounds kind of magical. Well, of course, obviously, there's no magic. And just like evolution by natural selection, it's actually a very, very simple concept that can lead to absolutely astonishing results. To get to a very amazing and surprising results, you don't often you don't need very fancy mechanisms. You can have a very basic mechanism repeated over enough iterations to have amazing things. Yeah, I see a lot of analogies between machine learning, neural networks and evolution because of that, very simple concept leading to results that are so good that they're hard to believe simply because there's enough iterations of that very basic process. So how does that work? First, you need to decide on an architecture. An architecture that means some model. So if you use, for instance, Python, the programming language Python, you can use some deep learning framework, such as, for instance, PyTorch or TensorFlow. And those frameworks have a number of functions that allow you to set an architecture for your neural network. And I'll show schemes of what that looks like conceptually, but just think of it as some ways the data is going to flow through your model. So some little calculations. And that architecture doesn't change. That part is very similar to classic programming, where you just have a set of instructions that don't change. And then you have some parameters. And the parameters are just numbers. So they're weight and biases. They're just numbers through your architecture. And you can start with random numbers, or you can start with numbers that you get from some prior model because you know that they work well for the task that you want your model to achieve. And while the architecture doesn't work, your parameters will change through training. And this change of the parameter is where the training actually happens. Your model, which is the architecture plus parameter, will change because the parameter will become better and better for the task at hand through the process of training. So then you need your labeled data in the case of supervised learning. So you have your inputs and the label, for instance, images and tree or no tree as label. So we know the output, the labels associated with our input. So to make sure that you don't do what is called overfitting, you need to take a little bit of your data and put it aside as a test set. A test set usually contains about 20% of your data. And this is like absolutely critical because otherwise your model can learn very, very closely your training data and perform astonishingly well with your training data. But instead of learning the overall concept of what a tree is, it may learn idiosyncratic things that are only true in your particular training set. Like maybe, for instance, luck has it that all of your images in your training set have a little bit of a pale area in the bottom left corner, just a fluke. Well, maybe that if this is the case, your model, if you overfit, will perform very good. I meant to say, sorry, that little pale area by chance happens to be more often on pictures with trees than pictures without tree. Just a random thing, right? Random correlation. The model is going to learn, if you overfit, that images with a pale area in the bottom left corner of an image should have the label tree. Well, in fact, it's a spurious correlation. It's just a fluke that has nothing with tree. So your model is going to perform super well on the training set because it's going to say, oh yeah, that's a tree because there's this little pale spot. But if then you pass some data it has never seen on some other pictures, well, it's going to perform very poorly because it's not going to see a tree when the tree is there if there's no pale spot, and vice versa. So the keeping some test set aside allows you to ensure you're not overfitting your model. So you're going to play with this train set, so 80% of your data, and you will put the inputs, so for instance, the images, through your architecture along with those parameters that you have chosen either at random or from another model. And you get some predictions, right? This is like a classic program, input, puff, some program, and you get an output. Now, what's cool about our situation here is that we do know what the output should be because our data was labeled. So we can compare the predictions with the labels. And at first, of course, particularly if you have chosen random parameters, your predictions are going to be disastrous, right? There's no reason why your model should know what a tree is. So it's going to be terrible. And we calculate a train loss, which is a value that shows how well or how poorly your model does. And there are multiple ways to calculate a train loss, but in all of the ways that it's calculated, the better the model, the closer the train loss goes to zero. Could have been the other way around, but there's a convention that train loss calculates as the loss goes down, it means that your predictions are better. And so that loss can then be used to adjust the parameters. If you have a loss that goes down, that means that your parameters were a little bit better. If your loss goes up, that means that your parameters have actually moved in the wrong direction. And so by seeing how the train loss evolves, we can monitor our program, and we can the parameters can be adjusted. Now, this adjustment of the parameter, that is not done by a human. That is done by back propagation through the process of learning. And I will talk about that a little bit later. But this is the automated part of machine learning, this thing here, the adjustment of the parameters by the train loss. Now, of course, the parameters can only be adjusted a teeny bit at each iteration. And this is why machine learning is very computationally intensive, because you need a very big model to get good results. So your architecture is a big thing to start with. Then you need a lot of data. So you need a lot of those input images, for instance, in our case, but could be any kind of data. And then mostly you need a lot of those iterations here. You need to loop things very many times to get the parameters at a place where they actually work very well. And then at the end, this architecture plus parameter, once the training is over, can be considered as one classic program that is called the model. So the difference with the classic program is that instead of being written by a human, instead of being a set of instructions that a programmer has written, the programmer has written the architecture. It has set the values of the initial parameters, but then he has let the system, or she has left the system run over many iterations for the parameters to adjust themselves. So it's not like there has been some automated process in the writing of this model. But this model now is just like a software program. So you can pass it some inputs and get some predictions as you would any program. So this is why we have left 20% of our data to test. Now we get our test inputs. So those are data that the model has never seen. And we get some predictions. And because our test set was labeled, we have the taste labels. So we know the true value. And we can compare it with the predictions to get some test loss. And similar to the training loss, the lower the value, the closer to zero it is, the better our model is. So this is where you can ensure that you haven't run too many loops of training, doing overtraining or overfitting, and that your model wasn't doing fantastic on the training set by learning spurious correlations and actually doing terrible on the test set. So once you are satisfied with your model, if once the testing proved good enough for you, then you have a program, and then you can take it out in the world and use it. This is where you can pass real world unlabeled inputs and get outputs that you can use in some practical purpose. So for instance, in the very simple example of our classifier that can tell whether an image has a tree or not a tree, at this state, you can just put it somewhere, sell it, whatever, and then people using it are going to pass images through that model and be told whether it's a tree or not a tree. And obviously, that can be more exciting things than detecting trees. But that's the general concept. And this general concept was thought of in the 40s. It's an old concept, but can only now be really used because only now do we have the processing power to get somewhere in this training process. That's computationally expensive. So what are those neural networks? Like I said, you have to set some architecture. Okay, well, what does that mean? So those neural networks are loosely influenced by biological networks. And in biology, our brains or any nervous system is made of a bunch of neurons. And what neurons do really is to transmit electrical signals between each other. So you have those intertwined, super complex connected units that touch each other and can pass signals, electrical signals or not, based on information they receive. So they get a ton of information from a bunch of neurons that they are connected to through their dendrites. They process it, and then they fire or not information to the neurons they're connected to. So artificial neurons are very similar, except that they are just little calculating units. They're numbers with basic calculations. So the inputs, instead of being electrical signals, are just numbers, simple numbers. For instance, if you have your image of a tree, what is an image? Well, it's a bunch of pixels on a two-dimensional plane. So each pixel can have a value in red, green, and blue. So think of your image as a bunch of units on the plane. And each unit is a value for green, a value for red, and a value for blue. So you have 3 values for each pixel. So you can flatten all that and create a very long vector of input by squashing your image if you want, instead of having it in 2D, having it in a single dimension. And instead of having 3 values of colors on top of each other, have them, for instance, aligned by juxtaposing the vector for the red, the vector for the green, vector for the blue as one giant vector. So now those inputs get passed through, get multiplied by some weights, and the weights are those. If we look back to our schematic of the functioning of training, those weights are among the parameters. There are a number of parameters in a network. Some belong to the architecture, so those don't change, and they're called hyperparameters. But weights and biases are your training parameters. So they are values that will change over time. So the weights are multiplied to the inputs. You had a little bias. It's not represented in this scheme, but a little bias is being added to shift things a little bit, which helps with training. And then they're added up, and then you have some activation function that provides an output. So you have a number of numbers coming in and a number coming out, which at a high level functions in a similar way to a biological neuron, except that you have numbers instead of electrical signal. And all of these things are connected. So in biological systems, the way neurons are connected is just absolutely astonishingly complex. In artificial networks, the way these artificial neurons are connected with each other is becoming increasingly more complex as models are becoming more sophisticated, but we're nowhere near the complexity of biological models. So models have been increasing in size, and we now have some, like, the big models by Google and OpenAI and etc. They have a number of neurons that is incredibly big, and that matches the number of neurons of some simple organisms. But where we still lag way behind biological concepts is that the ways the neurons are connected to each other is much more simple. And so in the simplest design, the early design, you have a number of layers of neurons. Each little dot is one neuron, so one little calculation. And those are connected to neurons in the following layer up to some output. So you have an input layer, an output layer, and in the middle, you have a number of hidden layers. And the number of hidden layers determine the depth. So when we talk about deep learning, it has to do with that depth, that number of hidden layers. And that's also the width. So the architecture of even a simple network like that can be extremely variable. Number of networks, number of neurons, number of layers, width of those layers, etc. And this activation function that I talked about at the end of the neuron is just some math function, and many have been tested and many have been used, and we use better ones now than at the beginning, but the idea is the same, is to combine all of those inputs from the preceding neurons and transform all of that to some output that makes sense to the next layer. In biological neurons, you don't have a number, it's only an electrical signal, and that electrical signal doesn't change in its intensity. What changes is the frequency. So a strong signal in a biological system will increase the firing frequency. In an artificial system, the value is going to be greater based on this function, but there still are similarities. And so the process of learning in biological system, it's the building of connections between neurons, while in artificial neural networks, the process of learning is this process of optimization of the model through the tweaking of those weights and biases. So there are many types of neural network. The very, very simple ones, the initial one built in the late 40s was a single perceptron, and it only had a single input layer. So very few neurons, single hidden layer. So very basic architecture. And then nowadays we have some that are much, much, much more complex. But then we have developed some networks that are much more sophisticated. Because when you deal with images, for instance, you have a lot of spatial correlation in the structure. And as you increase the size of the data and then make model more powerful by increasing the number of layers and the number of neurons per layer, you end up having like absolutely like huge number of calculations to be done in each of those little calculating units. So there are ways to reduce the number of calculations by using spatial correlation. And so convolutional neural networks tend to compress the number of neurons through some techniques that give results that are as good while using much less computing power. So for instance, you can choose the biggest value of a pixel over an area, or the average, etc. Then some things are not spatially correlated, but temporally correlated. And that's the case, for instance, of human language. In human language, the way words follow each other is not random. It follows some pattern. So for the case of temporal correlations, recurrent neural networks were a thing. And they used some looping through some layers, some recurrence, and that allowed to achieve better performance. The problem with these systems is that these recurrences made parallelization difficult. And the way to run large model, as I said, is to pass them through GPUs that can do these very basic calculations of, like multiplying the inputs by the weight, add the bias, do a sum, and then pass that through that little function. Those are very simple calculations, but there are millions of them. So if you can do them in parallel through multiple GPUs, that's okay. But if you have those recurrences, you can parallelize it easily. So recurrent neural networks have really fallen out of fashion because they're hard to render efficient. And so they have been replaced in the past 10 years or so by transformers. The T in ChatGPT stands for transformer. Transformers were initially invented by Google, and they involve multiple of those RNNs, so those recurrent neural networks, and those were bouncing data amongst each other. So by combining models, things got more complicated. But then someone came up with a very interesting concept that's called the concept of attention. And again, you can make analogies with our human brain or our biological brain. Our human brain or animal brains are very sophisticated. The computing power in, for instance, a human brain is huge. However, if we were to process continually every single stimulus that reaches it, our very big computing power would nevertheless be swamped, because we, like, imagine like all the stimuli you get from your body, from all your senses, from your own thoughts, like everything. It's just a lot. So how do we function? Well, natural selection has allowed us to totally subconsciously focus our attention on things that matter for our survival and our functioning. So we're not paying attention to every single stimuli. We are good at automatically detecting which ones are relevant and focus on those and process those. And so this was applied to artificial systems and with tremendous results. And adding this concept of attention, for instance, if we think of an image, think about that tree detection model again. Focusing on the sky, for instance, is not relevant as to whether there's a tree or not. So when there's a lot of big, uniform, bluish color near the top of the image, give very little weight to those pixels. So almost ignore them and give much more weight to things that are near the center of the image or that have a certain type of shape. That's what we do subconsciously. We give more weight, more attention to some stuff. And by increasing the weight of some data points that match some characteristics, people realize that transformers could perform as well without these recurrences. And removing the recurrences allowed to then parallelize those systems and run them very efficiently. And so now all of the very strong models all use transformers. So you might have heard of BERT. Well, the T in BERT is transformer. The T of GPT is also transformer. Now, of course, there are many limitations in those deep learning functionings. I'm not going to teach you everything in there. There's data bias if you use biased data, you're going to get very biased training, and your model is going to be very biased. It's very hard to fix these things. The machine certainly cannot. So you need to have some humans in the systems with some form of oversight, and it's not always easy. You can also have the subject that gets transformed, and that's not supposed to be how it works. For instance, all those algorithms that recommend things on YouTube or on social media, well, they're not supposed to transform us, but they are, and so that's also a problem. There have been bugs that can have life consequences. There are an increasing number of those. So, okay, lots of flaws there, and it's very problematic in a lot of situations. Now, what about NLP? I haven't said much about it, so let's talk a little bit about it. It's very similar, except that it uses human language as the data. So instead of having those pixels with tree or no tree, it's going to use language. How do we break it down? So, well, first, what is NLP used for? Well, many applications: spam detection and email filtering, human language translation, sentiment analysis, or classification of type of text. So like a very, very basic example, for instance, an NLP application, like a little model that can be built, is to be able to classify tweets as being positive or negative, like happy or sad. You know, very, very simple things. But of course, it can be much more powerful, such as in the case of predictive text, like autocomplete, or speech recognition, or increasingly actual natural language generation. That's what those very strong transformers these days are capable of doing. Chatbots, search results, etc. So the field of NLP with those powerful transformers has really exploded and is incredibly important. And when we talk about large language model, we are talking of those models that use NLP techniques, and often you actually have multiple models. So when we say a model, increasingly it's a number of models that are working together in some meta model, and that's what those big companies are developing, and that we see more and more around us. So how do we go from human speech or human written text to data that can be used in the way that our pixels from our images could be used? Well, first, there is tokenization, which is the production of tokens, that is like the production of units. So we need to break up the human language into units. So that can be done by splitting into sentences, sentence tokenization, or words, word tokenization. And of course, you don't do that by hand. There are tools to do that. There are algorithms that are capable of, for instance, using the spaces to do word tokenization, or the dots, I mean the periods, to do sentence tokenization. And for instance, if you want to do that in Python, there are a number of libraries that have a number of algorithms that can do all of these things easily. Then you need to remove the punctuation, because we want to extract the meaning of some text. And yes, punctuation does matter a lot for meaning, but where we are at in processing human speech, we need to do a bit of a rough work. We cannot focus on tiny details. So we remove the punctuation. We also remove stop words. So stop words are all of those words that are so common in a language. In the English language, for instance, that would be of, the, a, and, is, are, because they're so common that you cannot, they're not useful in classifying whether a twist is going to be positive or negative, for instance, because there's going to be a ton of these stop words in both categories. And the meaning of speech can usually be preserved without all of those little stop words. And again, this is not done manually. This is automated by some tools. Then you don't want the same word being considered as two different words if it is at the beginning of a sentence with a capital letter and if it's not. So everything is put to either uppercase or lowercase, but everything is kind of standardized. And then there is lemmatization. A lemma is kind of like the root of a word once you've removed the ed that show the past, the s that show the plural. So let's start with stemming. Stemming is really you take a word and you snap the end and you keep the root. So for instance, he walks, the root is walk and the s goes out. He walked, same thing. Walk is the root and the ed goes off. Because if the idea is walking, walks, and walked, we want to have this concept of walk. So that's called stemming when you keep the root. But stemming it uses very basic algorithm. It's fairly primitive, and it can lead to mistakes when you have words that get chopped too much. Footwear, for instance, could be chopped at foot because in the case of stemming, the algorithm sees foot as a word someplace. So okay, so that's a root. So then footwear, okay, foot is the root. And you lose the word footwear, which is a different concept. So footwear would be a lemma. And to not have footwear chopped to foot, but be kept as footwear, the process is called lemmatization, and it uses a more sophisticated algorithm that has been trained on some data and can use some context to be able to do a less rough job of removing the endings. So you end up with a bunch of lemma, which are concepts. Then you can identify word collocations that are group of words that should be considered together. For instance, United States, well, if you had United one place and then States another, you would lose the idea of United States, which is one concept. So how does word collocations work? Collocations works well through your text, all of those tokens. So say if we use the word tokenization, all of those words are paired in groups. So bigrams would be groups of two. So if you have the US is a big country, you would have, the United States is a big country, you would have the United is a bigram. United States is a bigram. States is a bigram. Is and actually would have been removed because they're stop words, but you would have states big is a bigram and big country is a bigram. And you do that, of course, over a lot of data, and then you look at bigrams that come up a lot more often than would be expected by chance. And if you have enough text, the bigram United States will be a lot, the frequency of the bigram United States will be a lot higher than the frequency of states big, for instance. So that's how you identify important bigrams that have some kind of unit sense. And then you do the same as a trigram, because there are groups of three that form some kind of meaningful unit, or any n grams. And there's some statistics running behind that allow to find those collocations of word. Then there's tagging that can be done to tag all of those collocations, and you end up with all of those concepts, and that's the data that you can then use to train your model. So up to tagging, this is machine learning, but doesn't involve deep learning, and you can from there do some statistics on all of these things. And that has been done for decades. Of course, now we have more data and we have more computing power for that too, but up to here, this is machine learning and statistics. But now we can also process this data through deep learning and apply the whole training process I showed like at the beginning of the hour on this human language data. So what kind of tools can you use to do these things? There are very many, and a lot of them are Python libraries. So if you are interested in machine learning, deep learning, or NLP, Python is a pretty good language. R has a lot of things also for the NLP side that is not going to use deep learning. But as I mentioned yesterday, R is too slow a language for deep learning. So yeah, if you're interested in this sort of field, Python is a pretty good language to learn. So there are some libraries such as scikit-learn that allow you to do some classic machine learning. And then there are some that allow you to do some deep learning, so using neural network, such as PyTorch. So PyTorch has Torch text, which is the part of the project that has to do with text, obviously. And then there are many layers that build on top of that, such as PyTorch NLP. There is NLTK, which is a suite of Python libraries that's really cool and allows to do all of those things I mentioned here, like the tokenization, removing the stop words, lemmatization. All of these things can be done nicely with the NLTK toolkit. There's Spacey as well. So there's a lot of packages that provide functions that allow to do all of these things. And which one to choose? Well, I very, very, very strongly suggest that you choose an open source tool versus something like MATLAB that is proprietary. It allows you to be able to still access your data and utilize your knowledge once you leave the university that has been paying for a license. It allows you to publish data that can be replicated, papers and methodologies that can be replicated in countries where they don't have rich universities that can pay for those licenses, or by independent researchers or by non-researchers. It allows you to look at the code if you want, so that you know what's in there instead of having some kind of mysterious black box. It ensures that there is a long-term access to your data, and you don't get locked into some proprietary thing that you may lose access to or may just disappear altogether, etc., etc. But then beyond that, choose tools that people around you are using. And as I said, Python is very useful for a lot of NLP work. And then there are a number of resources that you can watch later on if you are interested. I very strongly suggest that you watch those little videos. They're very short, they're very fun, they're excellent. And if you want to understand this process of learning and how the data works through a neural network, they really explain it beautifully with some very nice visualizations. They're fun and they're absolutely amazing. I really, really suggest you watch those. They're really good. And then if you want to have access to the literature, there's a lot of open access preprints when it comes to machine learning. Machine learning is really out in the open a lot, which is cool, except of course for those big companies, including OpenAI, which is one of the most closed ones. And then there's a couple of links, and Stack Overflow, of course, can be helpful if you look at all of those tags. Open data sets, data is very useful. So those links contain many links to countless open data sets. So that can be very useful. and then some documentation for various tools. So yeah, lots of resources if you want to browse.